Hello deep learners, welcome to this fifth lecture of PyTorch Zero to Hero playlist where we are going to learn about datasets and data loaders. So take a pen and paper, grab a hot cup of coffee and let's get started. So in the previous lecture, we built our first neural network and we simply followed this pipeline. So at first we loaded our dataset, then we splitted our features and labels, then we did a train test split. So we got our train data and we got our testing data. Then we applied standard scaling in order to normalize our inputs. And then we made torch tensors. So now we got the train and test features and labels. Now we made PyTorch tensors so that we can work in PyTorch. And lastly, we wrote our training loop where we simply trained our model for a finite number of epochs. So this was how it was done. So we imported the packages. We simply made a dummy classification dataset. We did train test split. We did standard scaling. We made PyTorch tensors. And then all the way up till here, we coded our neural network class using the NN module. So here we coded it. This is our network. And then we created a model object. Then we wrote our loss function, which was BC binary cross entropy loss. Then we wrote our Adam optimizer from our optim package from PyTorch. And then this was our training loop. So we ran a loop for a finite number of epochs. We toggled the model status to training with this line. Then we simply did forward propagation, loss calculation, and then all the following steps. But the thing to notice over here is this. As you can see in the forward pass, we passed the whole data set. So as you can see over here, we passed the entire training data into this model. And also while comparing, we compared this y hat, which is this, with the whole Y training data, with the whole label of the training data. So you can say that we are using here the entire data set, right? And then we are making a parameter update. Alright, now let's see. So in the previous lecture we saw this. So we did this and we just talked about this. But the thing is that, or the flaw you can say, is that we are using batch gradient descent, which means that we are using the entire data set for training. So as you can see, this step, this one and this one, we are passing the entire training data. So what is happening is we are using the entire training data for training. And so we got this section in Y train, which is our entire training data. And we are using this entire training data for simply doing this forward propagation, this loss calculation, this gradients compute, and lastly making the parameters update. Now what is happening is we are using this entire data set. Why? To just make one parameters update. Now that is the concept of our batch gradient descent. So this is the concept of our batch gradient descent. Now what's the problem with this batch gradient descent? So the problem is that we are loading this entire data set at once in our memory. So as you can see, we are using here this X train and Y train. So for using this, the entire data, it has to be loaded in the memory. That's why it is memory inefficient. Meaning that let's say you have a data set of lots of GBs, suppose 12, 15 GBs. Then you have to load this entire data set at once. And that will be like very under optimized in terms of your memory. And also we are using this entire data set to just make one parameter update, which means that we are making very less frequent updates. And that is why convergence becomes slower. Now what is this convergence? This convergence means that simply we have this loss function. So let me say this is our loss function. Now the goal of our neural network is to simply minimize this, right? or to find a minimal loss function. Now that is meant by convergence. So if you are making very less frequent updates, then convergence will be slower, which means we will reach this minima very slowly. Alright, now what's a better approach? So a better approach is mini-batch gradient descent. Now what is this? So the concept is simple. Instead of using this entire dataset, what we do is we divide this entire dataset into mini batches or chunks of data, and we process each mini batch and update parameters based on them. Meaning that for each epoch, what we are doing is we are running another loop for each batch, right? For each batch or chunk, you can say, and inside this we are doing the training code. So we are modifying the training loop. Now what is this batch? So let's say that you have 1000 rows. Now let's say that you want a batch size of 100. So how many will be your number of batches? Simple. It's the total number of data rows, which are 1000, by the batch size, right? Which is 100. So this becomes 10, which means that number of batches becomes 10. So what's happening is, for each batch, right, from 0 to 9, you are doing forward propagation, you're doing loss calculation, you're doing gradients compute, you're updating the parameters, but you will not be passing this entire dataset. Instead, what you will do is you will pass the dataset of this mini batch, or of this batch, you can say, of this ith batch. So that is simply the concept of mini batch gradient descent. So as you can see, we are processing and training our neural network on each of these mini batches iteratively, and simply this thing we continue for number of epochs we have. So let's say our number of epochs is 10, so for 10 times we do this thing. So that's the simple concept. So what is happening is we are making one parameter update per each mini batch. So let me say that the number of epochs is 10, and let me say that the number of batches over here is 10. So number of batches is again 10. Now what we are saying is that we first run a loop for number of epochs. So this is for number of epochs, meaning that this runs for 10 times because our number of epochs is 10, and inside this we run another loop for this number of batches times, or you can say for the total batches we have. So over here it is 10, right? So again we run this for number of batch times, which is again 10, and inside this we do our training thing. So simply in each batch we are doing one parameter update. So that's why we have total 10 batches. So in each epoch we are doing 10 updates, right? And similarly for 10 epochs we are going to do 10 times 10, which means 100 updates, right? So earlier, in case of this batch gradient descent, as you can see, we are running this loop for only number of epoch times, which means only 10 times. But now with this mini batch gradient descent, we are making 100 parameter updates. So you can see that it is much more frequent updates, right? And that's why convergence is much faster in this case. So let me say that total number of rows is 100 and batch size is 20. So number of batches will be obviously 100 divided by 20, which is nothing but here 5, right? So you have this model, and this is the scenario of each epoch. So first you have your model, and there are total 5 batches. So let me say they are batch 1, batch 2, batch 3, batch 4 and batch 5. So what is happening is, in each epoch you have your model. So you train this model on this batch 1. So it becomes this. I mean, the model, as it got trained on this batch 1, now it has learned some features. Now you again train this on batch 2, and then you again train this on batch 3, and then you again train this model on batch 4, and then you again train it on batch 5, and then you get this final trained model, and this you repeat for number of epoch times. So how many epochs you have, that many times you continue this thing. So that's why the number of parameter updates will be much larger as compared to the batch gradient descent. So that is the beauty of mini batch gradient descent. Now we can implement this batch gradient descent, mini batch gradient descent, stochastic gradient descent, everything. We can implement it manually, but definitely it's not an efficient way, right? Why? Because let's see. So for manually batching our data, we need to write lots of manual code from scratch. And also that code will be different for different data sets. So let me say that you are working with ANNs, so you are working with this tabular data. Then in that case, you have to write some different code for batching of these data rows as compared to, let me say that you are working with CNN and you are working with images. Then your code has to be different and you have to write it for images. Then let me say that you are working with videos, then you have to write some different code for manually doing this data batching. So simply this data loading, it will be different and it requires different code for each of these use cases. Number 2 is that, let me say that you want to apply transforms and augmentations. Now what are this? So simply you can think of transforms and augmentations as like you are applying filters on your original data to get some new data. So let me say that you have an image of a cat. So let me say that this is a cat. Now you apply transforms, like you made this grayscale, you applied another transform of cropping it, then you resized it, then you rotated it a bit. Then you can see that from each image we are getting this image, we are getting this one, we are getting this one, we are getting this one. So earlier we had just one image, now we have 4 images, right? So we have artificially increased our data set. Why? Because data is limited, right? And that's why we apply transforms and augmentations to artificially increase our data set, so that the model, it learns better and it generalizes well. So the thing is that manually applying these transforms and augmentations is again not easy and a bit hectic also. Third, you have to write different code for different batching algorithms. So let me say that you want to do batch gradient descent, then you have to write some different code. Let me say that you want to do mini batch gradient descent, then you have to tweak a little bit with your code. Now let's say that you want to do stochastic gradient descent, then again your code has to be different. So for different techniques, you have to write different types of code in order to adapt according to these methods. Fourth, let's say that you want to shuffle your data and sample it. So again, it's not easy and you have to research a bit for doing this. Now why do you want to shuffle this data? So let me say that your data set is like this. So let's say that this first 10 images are of cat and then these 10 images are of dog, right? Now if you do train test split of let's say that training data is 90% and tested data is just 10%, then as you can see this 90% of the data, it will be your training data, and this remaining this 10% of data will be your testing data. But as you can see, this is very uneven. So in your training data, you got more cat images and a very little section of this dog images. But in this testing data, you got 0 cat images and you got only these dog images. So when you're going to train the model and evaluate it, the results, it will be very uneven and very like false, because it is not true, right? So what you do is, before training it, you simply shuffle your data, so that like you randomly shuffle this data. So now this becomes cat, maybe this becomes cat, this becomes dog, this becomes cat, this becomes dog, like you randomly shuffle this data so that this uneven nature doesn't occur. And lastly, let's say that you want to use GPU for parallelism. So let me say that you have 5 batches. Now you have GPU, so you want to train the model parallelly. So B1, so this is batch 1. Parallelly you want to train the model on batch 2, batch 3, batch 4, batch 5. So you want to do this parallelly using your GPU. So if you have to do this manually, then again it is exhausting and you have to research a bit. Otherwise you can't achieve this very easily. So those are the flaws when you are going to manually load, process and batch your data. And also this manual process of doing things, it is very unscalable, very inefficient and highly under optimized and very error prone, because you are doing it manually from scratch. And lastly, it is very exhausting. And it is very much like you are reinventing the wheel when there's already much options available. And this option is nothing but your dataset and Dataloader that PyTorch provides us. Alright, so what's this dataset? So dataset is provided by PyTorch and its task is simple. It is used to load our data from the memory, and it yields, or you can say it gives or returns each data row or sample or entry iteratively, one by one, from this data located in the memory. So the thing is simple. You simply code a dataset class, like a custom dataset class. So it's like a blueprint or a template that decides how data is loaded. So it decides how data is loaded, from where data is loaded, and then it processes it, which means that in that class you can apply your transforms, you can apply your argumentations, your augmentations, your everything. So meaning that you code a custom dataset class inheriting from this dataset which is provided by PyTorch. And in that custom dataset class, these 3 things are to be provided. So first is the init. So this tells or determines how data is loaded. Number 2 is length. So this simply returns a number which is the length of the whole dataset. So it tells the PyTorch dataset module that how many total number of data rows or samples are there. And number 3 is the get item, which simply returns the data at the ith index, meaning that it takes an input of I and it returns the data row at the ith index. Alright, and now what is this data loader? So this data loader is simple. So the dataset class, it has direct access to the data in the memory, right? And this dataset class, it accesses the data and like it loads the data, right? So you can say that this dataset class, it loads data. And this data loader, it does batch generation, it does data processing, shuffling, sampling, enables GPU for parallelly loading the batches. So our dataset class, it gives our data row iteratively, and this data loader, it gets the one by one data rows from this data set, and this data loader, it produces batches out of them, and these batches are simply supplied by this data loader, or you can say that these batches are provided by this data loader to our training and evaluation loop. Simple. So this dataset class, it loads the data from our data in the memory, and it gives the data row one by one. And now this data loader, it gets one by one data rows using this dataset class, and it produces batches out of them. And finally, these batches, they are provided by this data loader to the training and evaluation loop. So this is the process. So let me say the total number of data rows is 8 and batch size is 2. So number of batches is simple, it's 8 by 2, and that's why it is 4. Alright. Now this dataset class, it provides all the data rows. How many data rows? 8 data rows to this data loader. So let's say that the IDs of the data rows are from 0 to 7 because there are total of 8 data rows. So it provides each data row to this data loader. And this data loader, it uses a sampler. So it uses a sampler which shuffles this data coming from the dataset class. So now we have this IDs of the data rows. So now we shuffled it. So now it became something like this. And then this data loader, it formed chunks or mini batches from these shuffled indices. So because the batch size was 2, so this became one batch, this became one batch, this became one batch, and this became one batch. Simple, right? And now for each index in this mini batch, so this 15, this 26, this 47, this 03, so each of this index in this mini batch, they are given to this dataset class, and this dataset class provides the data row like the sample or the entry located at this index. So let's say that you gave this ID 1 to this dataset. In return, it gave you the data row present at this index. You gave 5. So now it gave you the data row at the 5th index. Right? And this you do with all the mini batches. So similarly, you do with 26, you do with 47, you do with 03. So you give the indices of 2 and 6 to this dataset class, and in return, it gave you the data rows present at this 2 and 6th index. Similarly, it works for 47 and 03. Now finally, these batches formed from the above step, they return to this training and evaluation loop where you train your neural network on these mini batches. So that's the simple concept of dataset and data loader. Now some important things related to this data loader. So first, we can use GPU for the whole data loading and batching process. Second, we can very easily shuffle our data using samplers. So this data loader, after getting the IDs of this data rows, it can do shuffling, right, using a sampler. And third, we have something known as a collate function, which determines how we are combining this list of data rows from the data set and are forming batches. So it's like this step, this one, where the data loader, it is forming batches. So this collate function, it simply determines how this batch formation is being done. And by default, this data loader, it uses a simple batch collation mechanism for batch formation, right? So you don't have to manually perform this batch formation. Instead, you are using the default collation function provided by the data loader, right? But yeah, you can always customize it according to your need. But generally, we don't customize it until and unless we are working with NLP related tasks where in our collate function we have to apply padding in order to ensure that all the text they're of a similar sequence length, right? So in this collate function we apply padding, but this only happens in this NLP task. Alright, now let's see in code how it's working. So we first imported some packages, right? Then we got our device. Then we made a very dummy data set of classification. We plotted it. Now we did train test split, standard scaling. We made the PyTorch tensors. Next, this is the important thing. So this is the custom dataset class. So for this you have to write this line. So from torch.utils.data you are importing two packages, the dataset and the Dataloader. So you write a custom dataset class which inherits from this dataset, and inside this class you write three functions: this init function, len function and getAttempt function. So this init function, it takes these features and labels, which is nothing but your x and y, and it assigns it to this self.features and self.labels. Next, in this len function you have to return the number of data rows present. So you simply do self.features.shape because it's a tensor, and you do the 0th index because the 0th index is nothing but this one. Yeah, this one, which is simply the number of rows present, and this one is the number of columns or features present, right? So you take this 0th index, and inside this getAttempt function you take a parameter of index and you return the feature and the label present at this index. So you return this feature at this index and you return the label present at this index. So that is the simple custom dataset class. Now you create dataset objects. So train dataset is equals to custom datasets, this one. So now this is a constructor. So here you have to pass two things, features and labels. So you pass your xtrain and ytrain, and the same thing you do with your test data, right? So you pass your xtest and your ytest. Now you can see the len of this training data and the len of this testing data. So when you call this len function, it simply calls this one. So you can see that the length is 400, meaning that in this train data set there are 400 data rows, and in this test data there are 100 data rows. And then you create your data loaders. But before that, let's see this thing. So in this data loader there are some important parameters. So first is this data set. So here you have to mention the dataset object which you have created, so that this data loader, it can extract data and it can make batches. So you have to mention this data set. So for creating this train loader, you called this data loader, and inside this you passed this train dataset object which you created over here. Next you pass a batch size. So this is the chunk size or the size of the mini batch, you can say. So over here you're passing a batch size of 32. Then you have to pass shuffle. So this is a boolean, so this is either true or false. So it decides whether to shuffle your data coming from the dataset class. So here you did shuffle equals true, and then you have this pin memory, which is again a boolean, so it is either true or false, which decides whether to use GPU for this data loading and like for this entire data process. So here you give pin memory is equals torch.coda.is available. So you're checking if coda is available, and this returns a boolean, right? So first you create this train loader with the help of this data loader and you pass the train dataset object as the dataset, and you create this test loader where you pass your test dataset object as the dataset. So that's how you create these data loaders. Then you do this modeling, which is very simple. Then you create a model object. Then you define some parameters, and these things we have seen already. Now this is the training loop. So now what is happening is that for number of epoch times, you are initializing a variable with 0, which simply calculates the average loss for this epoch. So now then you put your model on this training mode. Now you iterate over these batches. So for batch features, batch labels in train loader. So I told before that you first run a loop for number of epoch times, then inside it you run another loop for number of batch times. So this runs for number of batches present in your train loader. So what is happening is you are getting one by one batch data. So first you got batch 1, then batch 2, then batch 3, then up till the number of batches your data loader has. Then after getting this batch features and batch labels, you move them to your device, because earlier you passed the model, because earlier you transformed the model to this device. So the same thing you do with this batch features and labels, so that all the computations regarding this model with this batch features and batch labels, they happen on the same device. So let's say that you're working on CPU, then this model, batch features and batch labels, they're all present at CPU. Let's say if you're using GPU, then this model, batch features and batch labels, they're all present at this GPU. So you move them to this device, then you do forward propagation. So y hat is equals to model, and you pass this batch features into this. Then you calculate loss for this y hat with this batch labels. So you are using this batch features and batch labels for doing forward propagation and loss calculation. Then you zero out the gradients. You compute the gradients using this loss.backward, and then you update your parameters. And at the end, you accumulate this loss. So this loss is nothing but the loss for this current batch, right? So you accumulate it, and this whole process, it runs for number of batches that are present in each epoch. And at the end of the epoch, what you do is you calculate the average loss using this total loss divided by the length of this train loader. So this length of train loader is nothing but the number of batches. So what you do is you are dividing this total accumulated loss with the total number of batches present, and that gives you the average loss for this epoch, right? And then you also print it at the very last. So that is simply the training loop. And for the evaluation loop, you do the same thing. So you iterate over this test batches. So you create batch features and batch labels for this test loader. You move them into this device. You do forward pass on this batch features, and then you calculate this y preds and you append them. So like everything is same, but you do this extra thing, which is you are dividing your whole data into mini batches, and then you are processing on these mini batches individually. So that is the concept of this mini batch, and that is how we use this dataset and data loader provided by PyTorch. And lastly, there are some more important parameters for this data loader. So there is one num workers which decides how many cores you want to use or how many GPU cores you want to use for this entire data loading process or data batching process. So here if you have GPU, then you can tweak with this number and you can see like how you can optimally use your GPU for fastening up this entire data loading, batching and processing. Then you got another parameter, which is this drop last, which decides, so this is again a true or false, and this decides whether to drop the last batch if it's incomplete. So let's say that total number of rows is 22 and batch size is 3, then simply 7 batches will be formed, right? So 1, 2, 3, 4, 5, 6, 7. So here there will be 3, here there will be 3, here also 3. Like in this entire part there will be 3, except this last batch which will have 2 data rows. So you can see that it has 2 data rows, whereas the batch size is 3. So you can see that this is an incomplete batch. So you can decide whether to drop this last batch, right? So if it has number of samples is less than the batch size mentioned, then you can decide if you want to drop this batch. But usually we don't drop it, right? Because it may have some importance. So we keep it and we train it as usual. Then we have this collate function, which simply decides how we are forming these batches out of this data rows IDs and nothing else. And this is by default provided by the data loader itself. So we don't play with it much. And lastly, we have this sampler, which is used for like shuffling the data. So let's say that you have your shuffle equals true over here. Then a random sampler is used, right, for sampling the data. Let's say that you have shuffle equals false. Then a sequential sampler is used, meaning that your data, it remains as it was and it is not shuffled. Now let's say that you have an imbalanced data set, then you can use a weighted sampler. But these things are a bit advanced and I would recommend that you research a bit because these are generally not used much. But yeah, like it depends according to our need, right? And then we can also code our own sampler, right? So there is a lot flexibility that Dataset and Dataloader provides us. Alright guys, so that's the whole concept of Dataset and Dataloader simplified for you. So in the next lecture, we are going to build our own handwritten digit recognition system in PyTorch, and it is going to be a lot fun because it is going to be entirely practical. So take a break and I'll see you in the next one.